I'm gonna go over 6.2, the second part. But before we get there, I should go over first part a little bit. So again, we are dealing with, once we got the first part, it's gonna make the second part a lot easier. So let's just do this actually. Let's say we have a function f of x, and we will set a boundary right here. So in chapter 4, we found how to find the area underneath this line, and obviously this is very simple, and we're just going to integrate f of x d of x, integrate from a, which is the starting point, and b, which is the ending point. But now we are rotating it around. Well, we're starting with the x-axis. So what we're going to do here is we're going to take this, and we are going to rotate it all the way around. It's not a great picture, but you get the idea. So now we are finding not area, but we are actually finding volume, because now we're dealing with 3 dimensions. So for here, we talked about we want to integrate from a to b, and since we are just taking a slice of this cylinder. So right here is just a disc that we're pulling out, and this disc actually has some depth to it. So we have, it's still in 3 dimensions, right? And this depth is just dx. So we're going to use, since this is a circle, right? If we pull this disc out, we're left with just a circle. So what we want to do is we're going to integrate the volume, which would be, so the volume is usually pi r squared times the depth. So I'll just do times depth. So now we're just going to plug in our function for r, because our function, right, from our axis to the line is just f of x. So our radius is just going to be our function. So we're doing pi f of x, and then our depth is d of x, like we just talked about. So that's what the first part is talking about. We're adding something a little different. For the second part, we're adding another line. So let's say we have g of x right here. G of x, we're rotating g of x around as well. As you can see, when we rotate g of x around, we get, and we slice it, we no longer get a disc, we get something different. We get a washer. So we're looking at something more along the lines of this right here, where this space in the middle is nothing. We're trying to find this volume, because again, this is 3-dimensional, right? So we're trying to find the full volume of the washer. And so I have a roll of duct tape as my representation. So we started off with just a line, right? Imagine, here, I'll line this up right. Imagine that this pen is the x-axis. And so when we originally graphed it, we got this, right? But now we are rotating it. We're rotating this rectangle around the x-axis. So we get something more along the lines of this. And as you can see, it's like a washer, right? We have an outer radius and an inner radius of our washer. And the way we're going to solve the volume of this washer is by subtracting this inner, I use green, we're subtracting the inner from the outer. So we're going to take a to b again, or is our interval from a to b. we're going to do pi, and we have to, sorry, that should be squared. So when we're dealing with volume of a washer, we're going to take one radius squared minus another radius squared times the depth. So big R is the outer, little r is the inner. So we're going to apply this same type of concept to the integration here. So pi f of x squared minus g of x squared. So again, we've kind of already covered this. I just wanted to review it before we jump into the more complicated stuff. So on that note, let us talk about revolving around something other than the x-axis. So we'll look at 14. We've spent enough time on it that I feel comfortable just walking through it with you guys. So number 14, 6.2, and we are given y equals 6 minus 2x minus x squared, and another y equals x plus 6. So I'm actually going to just plug this into the calculator to help me visualize what this is going to look like. Okay, so what we want to do is we want to take this spot where the two graphs overlap. That's the area that we're trying to find. So if we look back at our graph, I've got to expand it out this way a little bit. We have something like this. This is going to be f of x. And then we have a line coming up through here like this. Oops. This is going to be g of x. And we are trying to find this volume after we rotate it around something. So for A, we're just rotating it around the x-axis, which is down here. So what that's going to look like is a little sliver like this, rotated it around here. So it kind of is a weird, funky looking shape. So we get the idea that we're going for. So again, we're trying to find the blue. So we first need to find out when they intersect. So we need these intersection points are going to be our interval. So we're going to set 6 minus 2x minus x squared equal to x plus 6. So here we go. I like doing it this way. 6 minus 6 equals x plus 2x plus x squared. So this is going to go to 0 for 3x plus x squared. And so we know x equals 0, right? If we plug in 0 for x here, we get a 0, and we know the other value will be -3. -3 for x here will give us a -9 plus a +9, which will give us 0. So we know the interval is going to be from negative 3, right? We go left to right, negative 3 to 0. Now we're going to take our, so this is, so we're going to take f of x, or we're going to take pi r of x squared minus little r of x squared times dx. So again, dx is just the minute, or the infinitely small thinness of our disks. And this integration sign basically means we're going to add up all those tiny little disks to find the volume. So we have to figure out which one is going to be r of x. And we're always going to take the outer, the top, or the outermost is going to be the capital R. The innermost is going to be the lowercase r. So the outermost is this one here. So that's going to be my capital R of x, negative 3, 0, pi. So we're going to just plug that in. I'll use brackets. 6 minus 2x minus